Yes, power transformers of 480 volts primary have a short circuit rating. The short circuit rating is not typically marked on transformers because firstly, transformers have limited space available for markings. Secondly, high fault currents can be dangerous, and marking the rating may encourage improper handling. Thirdly, industry standards for transformer labels do not require the inclusion of short circuit ratings. When a transformer is subjected to high fault currents, the following occurs. Firstly, the transformer windings experience excessive current, leading to overheating and potential damage. Secondly, the high currents generate strong magnetic forces that can deform or damage the transformer core and windings. Thirdly, the high current can cause arcing within the transformer, leading to insulation breakdown and further damage. Fourthly, the transformer can fail to provide power or may become permanently damaged, requiring replacement. And fifthly, in severe cases, high fault currents can cause the transformer to overheat, catch fire, or even explode. The short circuit rating of a transformer indicates the maximum fault current it can withstand for a specified duration, usually 1 or 2 seconds, without sustaining catastrophic damage. It is important to ensure that the transformer is rated for the maximum fault current expected in the system. The short circuit rating can be determined through firstly, consult the transformer manufacturer's catalog, secondly, calculate the maximum fault current based on the system configuration and protection devices, and thirdly, conduct a detailed power system study to analyze fault currents and select an appropriate transformer rating. A transformer's ability to withstand short circuit currents is a crucial aspect of its design and application. Understanding the factors influencing this rating and the potential consequences of exceeding it is vital for ensuring the safe and reliable operation of electrical power systems. The short circuit rating represents the maximum current a transformer can handle for a limited time without sustaining permanent damage. This duration is typically specified, often as 1 or 2 seconds. Exceeding this rating can lead to a variety of detrimental effects, ranging from insulation degradation to catastrophic failure. The absence of a marked short circuit rating on the transformer itself is due to a combination of factors. Space constraints on the nameplate limit the amount of information that can be displayed. Safety considerations dictate that detailed fault current information should be handled by qualified engineers rather than being readily accessible to trained personnel. Industry standards do not mandate the inclusion of this rating on the transformer label, placing the onus on system designers to determine the appropriate rating based on the specific application. When a transformer is subjected to high fault currents, a cascade of events can unfold. Firstly, the windings experience excessive current flow, leading to rapid heating. This thermal stress can degrade the insulation surrounding the conductors, reducing its dielectric strength and increasing the risk of insulation failure. Secondly, the high currents generate intense magnetic fields that exert significant mechanical forces on the transformer core and windings. These forces can cause deformation, displacement, and even fracture of the internal components, particularly the winding conductors and their supports. Thirdly, the elevated current levels can initiate arcing within the transformer. Arcing occurs when the voltage exceeds the dielectric strength of the insulating medium, creating a conductive path through the air or oil. Arcing generates intense heat, further damaging the insulation and potentially leading to a short circuit between windings or to ground. Fourthly, the cumulative effects of overheating, mechanical stress, and arcing can result in a loss of functionality. The transformer may no longer be able to provide power at its rated voltage and current, or it may experience a complete failure, requiring immediate replacement. Fifthly, in extreme scenarios, the combination of high temperatures, arcing, and flammable insulating materials can lead to a fire or explosion. This poses a significant safety hazard and can cause extensive damage to surrounding equipment and facilities. Determining the appropriate short-circuit rating for a transformer involves a combination of methods. Firstly, the manufacturer's catalog provides detailed specifications for each transformer model, including its short-circuit withstand capability. This information is based on design calculations and testing performed by the manufacturer. Secondly, engineering calculations are essential for determining the maximum fault current that a transformer may experience in a specific application. These calculations take into account the source impedance, transformer impedance, and the impedance of downstream components. The calculated fault current must be less than or equal to the transformer's short circuit rating. Thirdly, power system studies provide a comprehensive analysis of fault currents throughout the entire electrical system. These studies utilize sophisticated software tools to simulate various fault scenarios and identify potential weaknesses in the system. The results of these studies can be used to select transformers with appropriate short circuit ratings and to coordinate protective devices such as circuit breakers and fuses. To further elaborate on the potential consequences of high fault currents, firstly, insulation breakdown is a primary concern. Transformer windings are insulated with materials such as paper, varnish, or epoxy. These materials are designed to withstand specific voltage stresses and operating temperatures. Excessive current flow can cause these materials to degrade rapidly, leading to a reduction in their dielectric strength. This can result in arcing between windings or to ground, causing a short circuit. Secondly, winding deformation can occur due to the intense magnetic forces generated by high fault currents. These forces can cause the windings to move, bend, or even collapse. This can damage the insulation and reduce the transformer's ability to withstand future faults. Thirdly, core damage is also possible. The transformer core is made of laminated steel sheets that are stacked together. High fault currents can cause these laminations to vibrate and loosen, which can increase core losses and reduce the transformer's efficiency. In severe cases, the core can even become damaged or distorted. Fourthly, bushing failure is another potential consequence. Bushings are used to connect the transformer windings to the external electrical system. They are designed to withstand high voltages and currents, but they can be damaged by excessive heat or mechanical stress. A failed bushing can cause a short circuit or ground fault, which can lead to a fire or explosion. Fifthly, oil contamination can occur in oil-filled transformers. The oil is used to insulate and cool the transformer windings. High fault currents can cause the oil to overheat and break down, which can lead to the formation of sludge and other contaminants. This can reduce the oil's insulating properties and increase the risk of insulation failure. Sixthly, fire and explosion are the most severe consequences of high fault currents. If the transformer insulation fails, it can cause a short circuit that generates intense heat. This heat can ignite the insulating materials, leading to a fire. If the fire is not extinguished quickly, it can cause the transformer to explode, which can cause extensive damage to surrounding equipment and pose a serious safety hazard. To mitigate the risks associated with high fault currents, several protective measures can be implemented. Firstly, overcurrent protection devices such as circuit breakers and fuses are essential for interrupting fault currents quickly and preventing damage to the transformer. These devices should be selected and coordinated to provide adequate protection for the transformer and the rest of the electrical system. Secondly, impedance can be used to limit fault currents. Increasing the impedance of the transformer or the electrical system can reduce the magnitude of fault currents and reduce the stress on the transformer. Thirdly, proper grounding is crucial for ensuring that fault currents are safely diverted to ground. A properly grounded system will provide a low impedance path for fault currents, which will help to reduce the voltage rise and prevent damage to equipment. Fourthly, regular maintenance and inspection can help to identify and correct potential problems before they lead to a fault. This includes inspecting the transformer for signs of damage, testing the insulation, and monitoring the oil quality. Fifthly, surge protection devices can be used to protect the transformer from voltage surges caused by lightning or switching operations. These devices will divert the surge current to ground, preventing it from damaging the transformer insulation. In summary, the short circuit rating of a transformer is a critical parameter that determines its ability to withstand fault currents without sustaining permanent damage. The absence of a marked rating on the transformer itself necessitates careful engineering calculations and power system studies to ensure that the transformer is adequately protected. Understanding the potential consequences of high fault currents and implementing appropriate protective measures is essential for ensuring the safe and reliable operation of electrical power systems. Furthermore, the selection of a transformer with an appropriate short-circuit rating is crucial for ensuring the safety and reliability of electrical systems. This selection process should take into account the following factors. Firstly, the maximum fault current that the transformer may experience in its application. Secondly, the duration of the fault current. Thirdly, the transformer's impedance. Fourthly, the type of protection devices used in the system. And fifthly, the environmental conditions in which the transformer will be operating. In addition to selecting a transformer with an appropriate short-circuit rating, it is also important to ensure that the transformer is properly installed and maintained. This includes ensuring that the transformer is properly grounded, that the connections are tight, and that the insulation is in good condition. Regular inspections and maintenance can help to identify and correct potential problems before they lead to a fault. Moreover, the location of the transformer plays a role in determining the required short-circuit rating. Transformers located closer to the source of power, such as a substation, will generally experience higher fault currents than transformers located further away. Therefore, transformers located closer to the source of power should have a higher short-circuit rating. The type of load connected to the transformer also affects the required short-circuit rating. Transformers that supply large motors or other inductive loads will experience higher fault currents than transformers that supply purely resistive loads. Therefore, transformers that supply inductive loads should have a higher short-circuit rating. The National Electrical Code, or NEC, provides guidance in the selection and installation of transformers, including requirements for short-circuit protection. NEC Section 450 covers transformers, and relevant sections within Article 450 address overcurrent protection and transformer characteristics. The NEC requires that transformers be protected against overcurrent by fuses or circuit breakers. The size of the overcurrent protection device must be selected based on the transformer's rated current and the type of load it supplies. The NEC also requires that transformers be installed in accordance with the manufacturer's instructions. This includes ensuring that the transformer is properly grounded, that the connections are tight, and that the insulation is in good condition. Additionally, coordination studies are essential in determining the appropriate settings for overcurrent protection devices to ensure selective tripping. This means that the protective device closest to the fault should trip first, minimizing the disruption to the electrical system. Coordination studies involve analyzing the time current characteristics of various protective devices to ensure that they operate in a coordinated manner. Power quality can also be affected by high fault currents. Voltage sags, which are temporary reductions in voltage, can occur during fault conditions. These voltage sags can disrupt the operation of sensitive electronic equipment. To mitigate the effects of voltage sags, it is important to select transformers with low impedance and to use voltage regulation equipment. Furthermore, harmonic distortion can also be caused by high fault currents. Harmonic distortion is the presence of unwanted frequencies in the electrical system. These harmonics can cause overheating of equipment and can interfere with the operation of sensitive electronic equipment. To mitigate the effects of harmonic distortion, it is important to use harmonic filters. In conclusion, understanding transformer short-circuit ratings, fault current calculations, and protective measures is essential for electrical engineers and technicians involved in the design, installation, and maintenance of power systems. A comprehensive approach that considers all these factors will ensure the safe and reliable operation of electrical equipment and minimize the risk of costly downtime and equipment damage. Continuous education and adherence to industry best practices are crucial for staying up to date with the latest advancements in transformer technology and protection methods.